continuing with our idea of series resonance, we now want to focus more on our current waveform. So I've copied this same RLC circuit that we were considering previously, and if we want to look at the magnitude of our current waveform, we can say that our current is this vector and we want to take the magnitude of it, so I'm going to set that equal to I. And we know in general that's going to be then the magnitude of our voltage, which is given as V sub m, divided by the magnitude of our impedance. And so that's our equivalent impedance, which includes our resistor, inductor, and capacitor. And so that was a complex value with A plus JB, where A and B are just some numbers. And so if we want the magnitude of that complex number, we do square root of A squared plus B squared. So from the equation we had in the previous video, we can then find the magnitude of our impedance as the square root of R squared plus the quantity of omega L minus 1 over omega C squared. So we get something that looks like this for our current magnitude. So let's plot this, and then we're going to use that plot to sort of further our discussion a little bit. So we're going to plot our current magnitude versus our frequency omega. And so what we talked about earlier is that when this imaginary part is going to 0, when it's canceling, the two components are canceling each other out, that's when we're going to have our maximum current magnitude. And as we can see, that magnitude is going to be equal to Vm over R. So let's put up a point over here. That's Vm over R. Okay, and we know that's going to be occurring for the case of our resonant frequency. So let's put sort of a dashed line here, and then I'm going to attempt to draw our current waveform. We notice that on either side of that resonant frequency, our current magnitude is decreasing. So we get something that looks like this. And so that should just be coming up and just touching that maximum value. I realize I've probably not drawn that very straight, but let's come over here and draw a couple more dashed lines. So this point here is going to correspond to our omega naught. For reasons that are going to become clear as we move on and talk about our filters, it's also useful to define a level right around here so we can sort of talk about a signal being in or out of this peak. So let me switch back to my solid line here. So we know this is our omega naught, and so actually switch back a little bit too soon. Let me come back here and put in a couple more dashed lines here so we can clearly indicate what these two frequencies are. Okay, so if we can call this omega 1 and omega 2. So once we get into talking about filters more, it's going to be important to say if a signal is between omega 1 and omega 2, then it's sort of in this peak area of our waveform. If it's below omega 1 or above omega 2, then it's not in sort of that peak area. So again, that will become more clear later on. So now a question is what is this level here that corresponds to our omega 1 and our omega 2? And so the answer is that it's kind of arbitrary. And in order to look into that, let's talk about our average power dissipated in the circuit. So our average power dissipated in our circuit is going to be given by P of j omega, so it's a function of frequency, and it's equal to 1/2 the magnitude of our current squared times R. And so again, this is just because this is an AC value, so if you have issues with where that comes from or you don't recall from previous classes with power, please let me know, we can go over that. So this would be sort of our general equation for our power dissipated. So let's say we want to investigate our case where we have our maximum current. So our maximum current, of course, we said occurs for the resonant frequency. So we're talking about P at j omega naught. And so we have the 1/2, and at that resonant frequency omega naught, our current magnitude is Vm over R. So we have Vm over R, square that quantity, and then we multiply by the R. We can clean this up a little bit if we want to bring that R from the outside in. We can say this is Vm squared divided by R. Okay, so again, like I said, it's kind of arbitrary as far as what we make this level, but let's say we make this level the half power level. So let's say we're interested in, well, let's put it this way. Let's say we're interested in frequencies where we have half of the maximum power. So 1/2 max power. And so that's going to correspond then to our omega 1 and omega 2. So let's say we want P of j omega 1 to equal P of j omega 2 to equal to 1/2 the power at the resonant frequency omega naught. Well, we just had an expression for that resonant frequency omega naught. So we can come down here and we can say, well, this 1/2 P of j omega naught is really equal to 1/2. And then from our expression up here, we can substitute in either one of these forms. So let's look at this one. We have another 1/2 times Vm over R, quantity squared, times R. And what we can do now is we can pull one of these 2's from our 1/2 inside this term here. And so of course, if we do that, we're going to need to put it under a square root. So we can say this is 1/2 times Vm divided by square root of 2 times R squared times R. So we get something that looks like this. So now what we can do is we can compare this back to this form here. And we can see that the term in the middle that's being squared corresponds to our current magnitude. So what we can say then is for our half power situation, so when we have half power, we have current magnitudes. So our current magnitude is I equals 1 over square root of 2 times the maximum current magnitude. So we can also write that as 1 over root 2 times Vm over R, which is approximately 0.707 times Vm over R. So what we can do then is we can come back up to this plot and we can say, well, now we know what this value is. We can say this is 1 over root 2 or 0.707 times our Vm over R. And so again, that selection was kind of arbitrary. That was just based on looking for areas where we had half of the maximum power. So in the next video, we're going to come back and we're going to talk in more detail about what this omega 1, omega 2 are and how they relate to some other important parameters that we use to describe this series resonance circuit.